Hello friends from wherever you are, welcome back to our today's lesson, and we are going on with the moment distribution method, and today we are given a fixed beam that is fixed on both of its ends and supported at its center, and we are supposed to plot its bending moment diagram as well as its shear force diagram. So as usual, please give us a subscription and we are going to appreciate so very much. Back to our video. Now we are going to begin with calculation of the fixed end moments, and in this case we have two spans, span AB as well as span BC. Span AB is loaded with a UDL of 2 kilonewtons per meter. Span BC is loaded with a point load at D of 12 kilonewtons. Now, the very first that we usually do when we are dealing with moment distribution method, we usually calculate the fixed end moments. And in this case, we are going to begin with span AB. And in span AB, the fixed end moment at A is going to be an anti-clockwise moment, and it will be given by this formula: negative W L1 squared divided by 12, since this span is loaded with a uniformly distributed load. Negative because the fixed end moment at A is an anti-clockwise moment, and therefore this is going to give us a W, which is 2 kilonewtons per meter, therefore negative 2 multiplied by L1, which is 6 meters, so 6 squared. We divide that by 12, and when we do so, we are going to get a fixed end moment at A of negative 6 kilonewton meter. Then from there we go to the fixed end moment at B in the span AB, and in this case the fixed end moment at B is going to be a clockwise moment, and therefore since it is a clockwise moment, we are going to apply this formula: positive W L1 squared divided by 12. This is going to be positive 2, that is the UDL, multiply by the span, which is 6 meters, so we square it, then we divide that by 12, and this is going to give us a fixed end moment at B, fixed moment of positive 6 kilonewtons meter. So we are done with the span AB. Then from there we go to the span BC, the span B to C. Therefore, in span BC, the fixed end moment at B is going to be an anti-clockwise moment, and it is going to be given by this formula: negative WL2 divided by 8, since this span is loaded with a point load. And this is going to give us negative W. W is a point load of 12 kilonewtons multiplied by L2, which is 6 meters, divided by 8. And when we do that, we are going to get a moment of negative 9 kilonewton meter. So that is the fixed end moment at B. Finally, the fixed end moment at the end C, the fixed end C, it is going to be a clockwise moment, and therefore it's going to be positive. So we are going to have positive WL2 divided by 8, and this is going to be positive W is 12 kilonewtons multiplied by the span 6 meters divided by 8, and that is going to give us a fixed end moment at C, moment of positive 9 kilonewtons meter. Then after calculating the fixed end moments at the two spans, the next thing we are going to do, we are going to determine the stiffness factors. So we go to stiffness factors. And in this case, we are going to have this. The stiffness factor, that is KBA, that is stiffness factor on this member BA, is going to be given by 4EI divided by L, since the end A is fixed. So that's the formula when an end is fixed. And this is going to be 4EI divided by L, which is 6 meters. When we simplify that, we are going to have 2 over 3 EI. Then we are going to determine the stiffness factor on the member B to C. And likewise, it is going to be given by this formula, 4EI divided by L, since the beam is fixed at the end C. And this is going to give us 4EI divided by the span. So this is L1, this is L2. They are the same. So we are going to have 2 over 3 EI. Then we are going to determine summation of the stiffness factors by adding the stiffness factor on member BA plus the stiffness factor on member B to C, and that is going to give us 2/3 of EI plus another 2/3 of EI, and that is going to give us 4 divided by 3 EI. Then after calculating the stiffness factors for those two members, the next thing we are going to determine is the distribution factors. So we go to distribution factors. Distribution factors. Likewise, we are going to begin with distribution factor for member BA. Member BA, and that's going to be given by the stiffness factor for member BA divided by the summation of the stiffness factors, which will be equal to, stiffness factor for member BA is 2/3 of EI. We divide that with the summation of stiffness factors, which is 4 over 3 EI. And this is going to give us 2 over 3 EI multiplied by the reciprocal of that, which will be 3 divided by 4 EI. The EI's are going to cancel out. The 3's are going to cancel out. By 2, 1, by 2, 2. And that's going to give us a half. Therefore, the distribution factor for member BA is going to be a half. 1 over 2. Awesome. Then we go to distribution factor for the member BC. Member BC, which will also be given by the stiffness factor for member BC divided by the summation of the stiffness factors. And this will be given by stiffness factor for member BC is 2/3 of EI. We divide this by 4 over 3 EI, which is the summation of stiffness factors. And this is going to give us 2/3 of EI multiplied by the reciprocal of this, which is 3 over 4. Let me write this 3 correctly. 3 over 4 EI. Video over 4 EI. And just like the distribution factor on the member BA, the distribution factor for member BC is also going to be a half. So we are done with the calculations of the distribution factors. The next thing we are going to do, we are going to draw the distribution table and determine the moments, that is the support moments, using the distribution table. So this is how our distribution table is going to look like. We are going to have joints, and in this case, on our beam, we have 3 joints, A, B, as well as C, which we have them there. Then down below the joints, we are going to have the spans. And for the joint A, we have the member AB, which is AB. For the joint B, on the left hand side, we are going to have member BA, which is here, and on the right hand side, we are going to have member BC, which is that. And for the joint C, we are going to have member CB on the left of C. Then the next, that is below the spans, we are going to have the distribution factors, and we have calculated them. Distribution factor for the member BA is a half, and that for the member BC is a half as well. So we write them below those 2 members. Then below the distribution factors, we have the fixed end moments, and we had calculated all the fixed end moments. They are here, so we are going to write them each on its member. Then from there, we are going to do what we call distribution. So we distribute. So distribute. And what we are distributing in this case, on the joint B, on member BA, we have, that is on joint B, the left hand side of B, we have positive 6. That is a clockwise moment of 6 kilonewton meter, and another anti-clockwise moment for the member BC. So here we have an excess bending, we have an excess moment of positive 3. Why positive 3? What we do to get the excess moment, we usually change the signs for these 2 fixed end moments, and therefore with the positive 6 is now going to be negative 6, and negative 9 is going to be positive 9, and that is going to give us an excess moment of positive 3 kilonewtons meter. Then we are going to distribute this moment by the distribution factors on each member. So on member BA, we are going to distribute this positive 3 kilonewton meter by the value of the distribution factor for the member BA, which is a half, and that's going to be 1.5 kilonewtons meter. For the member BC, we are going to do the same. We are going to distribute this excess moment with the distribution factor on the member BC, which is a half as well, and that's also going to be 1.5 kilonewtons meter. Therefore, here we have positive 1.5 kilonewtons meter, and on the member BC, we also have 1.5 kilonewtons meter. Then after distributing on both members, we are going to carry over. So carry over, in short, we are going to write it as CO. So we are going to carry over half of this moment to the joint A on member AB. So when we carry over half of 1.5, we are going to have positive 0.75. So that is the moment we are going to carry over to the joint A, just for balancing purposes. Likewise, on the joint C, we are going to carry over half of this moment to that joint, and therefore we are also going to have positive 0.75. That is half of 1.5. Remember, I said that the carryover factor is usually taken as a half. And then after carrying over, we are going to distribute again. So we distribute, but in this case we got nothing to distribute since on the member BC we don't have any moment, so we got nothing to distribute. So those are going to be, they are going to be zeros. And then we determine our final moments. So we go to final moments. And for us to get the final moments, we are going to add the fixed end moments plus the moments that we got below the fixed end moments. For example, on the member AB, on the joint A, we are going to have fixed end moment of -6 plus positive 0.75, and that is going to be -5.25 kilonewtons meter. Then for joint B, we are going to have 6 plus 1.5, which is positive 7.5 kilonewtons meter. And on the member BC, that is for joint B, we are going to have -9 plus 1.5, which is -7.5 kilonewtons meter. And then 9 plus 0.75, that is positive 9.75 kilonewtons meter. So those are now our final moments, that is the final support moments. Then after that, we are now going to calculate the maximum bending moment between the span AB, and for the span BC, the bending moment at the point D. So that will be our next thing to do. So we go to span AB. So for the span AB, span AB is loaded with a UDL of 2 kilonewtons per meter. Therefore, the maximum bending moment will be given by WL1 squared divided by 8. And this is going to be W 2 kilonewtons per meter, L1 6, therefore 6 squared, and then we divide that by 8. And when we do so, we are going to get a maximum bending moment of 9 kilonewtons meter. So that is the maximum bending moment for the span AB. Then we go to the span BC. So for span BC, for the span B to C, the bending moment at D, that is MD, will be given by WAB divided by L. And W is the point rod at D, which is 12 kilonewtons. A is the distance B to D, which is 3 meters. B is the distance D to C, which is 3 meters as well. And then we divide by L2, in this case it is L2, which is the span B to C, that is 6 meters. And when we do so, we are going to get a bending moment at D of 18 kilonewtons meter. So that is the bending moment at D. Now, after getting all the moments, that is the support moments as well as the moments due to vertical loads, we are now going to plot our bending moment diagram. And this is how it's going to look like. We got, let's start with the bending moments due to vertical loads, beginning with the span AB. So we have a moment of 9 kilonewtons meter. So let me approximate it to be at that point. And since the span AB is loaded with UDL, the BMD is going to be a smooth curve like the one I'm drawing here. So that will be the bending moment diagram with a moment of 9 kilonewtons meter. Then for the span BC, the bending moment at D, that is 18 kilonewtons meter. So 18 might go all the way up to that point. Yeah, just let me remove this reaction at C. Yeah, 18 might go all the way up to that point. So we are going to join this all the way. Where? No, Masana. So I'm going to join all the way there. Not bad. So we are going to join this all the way there, and then we join it to C. So join it to C. Good. So that is a bending moment diagram for the span BC, having a maximum bending moment of 18 kilonewtons meter. So that is it. Then after plotting the bending moment diagram due to vertical loads, we are now going to plot the bending moment diagram due to support moments. And beginning with the moment at A, we got negative 5.25. 5.25, let's say, is at that point. So here we have 5.25 kilonewtons meter. Then at B, we have 7.5. So 7.5, let's say it's there. So we are going to join this 5.25 with this 7.5 kilonewton meter. So here we got 7.5 kilonewtons meter. Then the bending moment at C is 9.75. So above 9, let's say there. So we are going to join 7.5. We join it to 9.75 kilonewtons meter, and then we drop that all the way to C. So that's how our bending moment diagram is going to look like, with this part being negative, this one is positive, this one is negative, this one is positive, and this one is negative. Then to complete our BMD, we are going to shade off its outline for it to become very clear, very smart, and visible. So that's now how our bending moment diagram will look like. Then after plotting our bending moment diagram, we are now going to plot the shear force diagram. But for us to plot the shear force diagram, we require the shear forces. And for us to get the shear forces, we must first of all calculate the values of the reaction. That's why I got here reaction at A, reaction at B, and at this point we are going to have reaction at C. Now, for reactions calculations, let's begin with the span AB, and in this case, for span AB, we are going to take moments about B. Therefore, take moments about the sample to B. And when we do that, we are going to have this. Remember, when we are calculating reactions, we must remember that the values of anti-clockwise moments must be equal to the sum of clockwise moments. And in this case, when we multiply RA multiplied by 6, that is when we take moments about B, that is going to be a clockwise moment. So we are going to have RA multiplied by the distance from A to B, which is 6 meters, and then the bending moment at B is also going to be a clockwise moment. So we are going to add it here. So we add bending moment at B is equals to anti-clockwise moments. The first anti-clockwise moment will be the bending moment at A, which in this case is 5.25. So we add MA plus, between the span A to B, we have a UDL of 2 kilonewtons per meter, multiplied by the span over which it is distributed, that is 6, and then we multiply by half of that span. Since this point rod of 2 times 6, we wrapped at the mid of that span. So we are going to advance to RA times 6 plus MB, which is 7.5 kilonewtons meter, is equals to bending moment at A, which is 5.25 kilonewtons per meter, plus 36. This will give us RA times 6 being equal to 5.25 plus 36, that is 41.25. Then we take 7.5, the other side of the equal sign is going to be minus 7.5. That will lead us to RA being equal to 41.25 minus 7.5, that is 33.75. And then we divide by this 6, and that is going to give us a reaction at A, reaction of 5.625 kilonewtons. So that is the reaction at A. After that, we go to the span BC. Therefore, for the span B to C, for span BC, take moments about B as well. Take moments about B. And when we take moments about B, we are going to have this anti-clockwise moment of RC times the distance from C to B, which is 6 meters. So that is going to be RC times 6 plus the moment, anti-clockwise moment at B of 7.5 kilonewtons meter. So we add MB. This is going to be equal to a clockwise moment at C, that is bending moment at C, MC, plus another clockwise moment of 12 times the distance from D to B, which is 3 meters. So that's going to be 12 times 3. This is going to lead us to RC times 6 plus MB, which is 7.5 kilonewtons meter, is equals MC, which is 9.75 plus 12 times 3, that is 36. This is going to give us RC times 6 being equal to 9.75 plus 36, that is 45.75. So 45.75. Then you take 7.5 the other side of the equal sign, that's going to be minus 7.5. Let me write the other part here. Yep. Then we are going to have this RC times 6 being equal to 45.75 minus 7.5, that happens to be 38.25. Therefore, 38.25. To get the value of RC, we are going to divide both sides by 6, and that is going to give us a reaction at C of 6.375 kilonewtons. Now, to get the reaction at B, we are going to say this: the sum of all the upward acting forces must be equal to the sum of all the downward acting forces. And I think this is Newton's third law of motion that states that for every action there must be an equal and opposite reaction. So we are going to have this upward acting forces or reactions. We have RA plus RB plus RC is equal to the downward acting forces. We have AB UDL of 2 times the span over which is distributed, that is 6. So that is 2 times 6. Then we add point load at D, which is 12 kilonewtons, so plus 12. RA is 5.625, so 5.625 plus RB plus RC, which is 6.375, is equals to 2 times 6, 12, plus 12, that is 24. And RB will be equal to 24 minus 5.625 plus 6.375, that is 12. And this is going to give us a reaction at B of 12 kilonewtons. So that is the reaction at B. Very good. Then we are going to write those reactions on our loaded beam. Starting with the reaction at A, 5.625. So we write there 5.625 kilonewtons. Reaction at B, we got it as 12 kilonewtons. Reaction at C, that is 6.375. Let me squeeze it here. 375 kilonewtons. Awesome. After getting the value of the reactions, the next thing will be shear force calculations. And I think it will be, I'll squeeze it there. Let me see whether it will be squeezable. So you go to SF calculations. So we go to shear force calculations, and I think this part will be enough for the shear forces. And we are going to begin with the shear force between C and D. So the shear force between C and D will be equivalent to the reaction at C, which is 6.375. So that is equals to 6.375 kilonewtons. Then from there you go to shear force between D and B. So shear force between D and B, that's going to be this 6.375 minus the point load at D, which is 12, and that is going to give us a shear force of negative 5.625 kilonewtons. Then from there we go to shear force at B. So shear force at B will be the shear force between D and B, which is negative 5.625 plus the reaction at B, which is 12 kilonewtons, and that's going to be equal to positive 6.375 kilonewtons. Then from there you go to shear force between B and A. So the shear force between B and A will be this shear force at B, which is 6.375 minus, between B and A we have a UDL of 2 kilonewtons per meter multiplied by the span over which it is distributed, that is 6. It is going to give us 12 kilonewtons. So we subtract 12 kilonewtons, and that is going to give us a shear force of negative 5.625 kilonewtons. Then finally, the shear force at A, it will be equivalent to the shear force between B and A, which is 5.625 kilonewtons. So that space was enough for all the shear forces. So we got the shear force between C and D, shear force between D and B, that is it. Shear force at B, that is it. Shear force between B and A, we got it there. And finally, shear force at A. Then, after getting the values of all our the shear forces, the final thing will be plotting the S.F.D. And we are going to begin with the shear force between C and D, which is 6.375. So 6.375, where is that point? So between C and D. So that's going to be a straight line. Then join it to C as well as at D. So this is 6.375 kilonewtons. Shear force between D and B, that is negative 5.625. So negative 5.625, let's say, is at that point. So between D and B, a horizontal line, join it to D, join it to B. So this is 5.625 kilonewtons. Shear force at B. Shear force at B, we got it as positive 6.7375. Guess is that point. So we have 6.375 kilonewtons. Then join it to the horizontal line. Then the shear force between B and A will change uniformly from 6.375 to negative 5.625. So guess at that point. So we are going to join this to this 5.625 kilonewtons, and we are going to join it with the diagonal line. And then shear force at A is 5.625. So this is a negative shear force, positive shear force, negative shear force, and positive shear force. Then to complete our S.F.D, we are going to shade off its outline for it to become clear, visible, smart, beautiful, etc., etc., etc. So ladies and gentlemen, that is how we plot the shear force diagram for such a fixed beam. So we appreciate so much for being part of our supporters, or being one of our supporters. And if you aren't yet to subscribe, please hit that subscription button as well as the notification bell, so that whenever we upload a new content, you will be notified. So let's meet in yet another lesson to continue with the moment distribution method. This is Kamiti. Thank you very much.